Welcome back. As you know, I am Eli, the computer guy, and in today's class, we're going to go over NAT, Network Address Translation, and TCP Port Forwarding. So we're gonna get back to subjects that the human brain can understand relatively easily. We just did the class on subnet masking, and I will tell you honestly, that class is as hard to teach as it is to learn. I don't know why. I honestly don't know why so many people have a problem with subnet masking. It's relatively simple. Basically, you look for all the ones. Wherever all the ones end, that's your subnet mask. Everything to the left-hand side of all the ones, that's your network identifier. Everything to the right-hand side of the ones, that is your computer identifier. It seems like it should be relatively easy. It is relatively easy. I just explained it. I just explained subnet masking. Oh, still melts my brain. Still melts my brain after all this time. Again, in the real world, how you actually deal with subnet masking in the real world is somebody will give you the numbers. Then you plug those numbers into your DHCP server and you go about your day. You don't actually sit there and subnet mask a lot in the real world. But if you're gonna be a professional, you do have to understand it. But thankfully today, that is not what we're gonna be talking about. Today we're gonna be talking about network address translation. And basically, network address translation is the technology that has kept us from migrating to IPv6. If you're sitting there right now and you're looking at the clock and you're saying, we're in the 2020s, why are we not yet using IPv6 in a major way? The reason is because of NAT, because of network address translation. So the reason that we need network address translation, and the reason that many of us thought we would be to IPv6 at this point in time, is because of a built-in failure for IPv4, where IPv4 can only have about 4,200,000,000 some odd IP addresses. So basically, individual IP addresses that are available to use for computers and devices. When they're going through and they were creating the subnet masks and they were creating that whole system, they were sitting there like, I wonder how many addresses we might possibly ever need. And so again, this was about 50 years ago when this technology started to get deployed. And so they said, you know what? We're just gonna go crazy. We are going to come up with a number that is so insanely big, we will never use all of those possible addresses. And so when they came up with TCP IP version 4, they came up with a system that could have 4,200,000,000 some odd IP addresses, and they said, there you go. The one thing we will never have to worry about is running out of IP addresses. But then we get to the modern world. We get to the modern world where instead of having like one computer per entire office building, or even one computer per house, we're in this world of IoT, the Internet of Things, where everything nowadays has an IP address. Your thermostat may have an IP address. Your smartwatch may have an IP address. Your smartphone may have an IP address. Your car may have an IP address. They were theorizing at one point, I think this is a little extreme. I don't believe we will get there. But they were talking about one point that they thought that each house might actually end up with 200 individual IP addresses. Basically, the idea being that everything in the house was going to be IP addressable, and so if you add all that up, you would have 200 devices per house, which would become a problem. Right? Because all of a sudden, 4,200,000,000 some odd unique IP addresses no longer seems enough, no longer is enough for all of the amount of devices that are going to be connected to the internet. And so they had to come up with a solution for the problem of this limited number of IP addresses. Now, the thought was, what I was told 22 years ago, when I got my MCSE in 2000, my MCSE NT 4.0 in 2000, what I was told back then is because we're going to run out of IP addresses, we're all going to be moving to IPv6. When you go to IPv6, there's literally almost a limitless amount of IP addresses based off of how IPv6 does its IP address scheme. So basically what we were all told is, hey, this IPv4 thing will die in the next few years and we'll go to IPv6. That was one thing to migrate over. But the problem was we had all this quote unquote legacy equipment. Back then, we had all this 30-year-old equipment that was built for Ethernet and TCP/IP version 4, and so they needed a solution in the quote unquote short term. Again, notice how in the technology world, how band-aids end up never getting pulled off. One of the things you have to think about with technology professionals is many times we tell people we're putting on a band-aid, and then we put it on and walk the hell away and never deal with it ever again. Anyways, one of the band-aids that was supposed to be put on is a NAT, this thing called NAT, Network Address Translation. And what NAT allows you to do is it allows hundreds or thousands of computers or devices to essentially use one external IP address. So you will hear about your external IP address and your internal IP address. So your computer inside your facility, inside your house or whatever else, might have an IP address of 192.168.1.10 or something like that. And you may have a lot of devices in your house at 192.168.1.20, 192.168.1.55, 200 devices may be in your house. They all connect into your router, and then your router has an external IP address. 205.66.55.4 or whatever, right? And basically what NAT does, Network Address Translation, is it allows all of the internal computer devices to be able to use that external IP address in order to communicate with other devices on the internet and other devices on other networks. So today we're going to be talking about Network Address Translation, and then also once you start dealing with Network Address Translation, you have to deal with something called TCP Port Forwarding, and that's what this class is going to be talking about today. Okay, so to really understand network address translation, one of the things we have to talk about is basically the world as it was when Ethernet and TCP/IP4 originally debuted. Again, one of the big problems that you'll start to see in our modern world of networking is that we are still using technology that has essentially been band-aided 1,000 times for the past 50 years. So think about this, right? So when Ethernet came out in 1973, that was literally before I was born. I am now in my mid-40s. It's not, it came out when I was young or it came out when I was in high school. Ethernet literally came out before I was even born. And in that world, the problems that the engineers were dealing with at that time looked a lot different than the problems that we're currently dealing with. And so one of the big things with Ethernet and one of the big things with TCP/IP version 4 is there was a question at that point in time of essentially what happens if it's a nuclear war? Oh, golly. If you're watching this in the timeline, you're going to know why that's kind of funny. You know the thought that way back 50 years ago, people were worried that Russia might try to nuke us. Oh, anyways, politics are not coming into class. Politics are not coming into class. Back then, though, what you have to realize is the communication world, the technology communication world that we're in at the time. So back then, we were essentially in a world of telephones. We had telephones, we had teletypes, essentially all the data communication, a lot of the data communication that was going on at the time, more or less were going through hardwired telephone lines. And so back then, with these hardwired telephone lines, you literally had a physical wire that went from point A to point B. If somebody was in Washington, D.C., and they're calling somebody in San Francisco, there was actually a hardwired connection that went all the way from point A to point B. So if you had somebody over here and they were in Washington, D.C., basically their phone line would connect to something called a central office. Their central office would connect to trunk lines that would basically get them over to the other side of the country. From the central office that was closest to the person in San Francisco, there would be a telephone line that would go to that particular person. And so you would actually have a hardwired connection all the way from point A to point B. And many times with this type of communication, there really was only one set of basically communication lines that would go through between central offices or these telco facilities to get from point A to point B. The concern back then was what happens if the USSR launches nuclear weapons at the United States and then destroys these central offices. And basically, the modern equivalent of that, the metaphorical equivalent of that, is essentially what if Russia put a backhoe through your T1 line, right? Since there are these hardwired connections and basically very limited hardwired connections to get these calls through, the communication through, basically if a bomb dropped on one of these central offices, you could not get communication from one place to the other, and folks realized that this was an issue. And so what they wanted out of Ethernet, what they wanted out of TCP/IP4 was a way to create a large autonomous routing network so that if there were failures in the network, the communication could essentially get routed around those failures and you could actually talk to the person on the other side. That's what we talk about with the cloud. Whenever you hear about the cloud, basically what the cloud is just a tremendous amount of networking equipment that's been installed around the country and now around the world that allows traffic to get routed from point A to point B, right? So if you're over here now in Washington, D.C., you're trying to communicate with somebody over in San Francisco, you're going to connect into the internet cloud, essentially. And with this cloud, you have a whole bunch of networking equipment and switches and all kinds of different things. And when you try to communicate with that person in San Francisco, your communication is going to go into one router. It's going to look to see in real time what the communication status is with other routers, and then auto route to the router it thinks is most appropriate, to the one it thinks is most appropriate, to the next one, and then out to the person that you're trying to communicate with. Right? Now with this, basically if you have a problem, so let's say Russia, drops some nuclear bombs here and destroys some major hubs of communication. Even though they've destroyed those major hubs of communication, when you try to communicate with that person in San Francisco, what's going on here? Person in San Francisco, what's going to happen is the communication is going to go up. The router is going to look to see which is the most appropriate router, send to the next router. That router is going to look to see the most appropriate router, and then when it finds it, it'll send, right? And so even as routers are essentially destroyed, as the system goes up and down, they will automatically create these new routes through the internet cloud so that people can communicate with each other. So if you have a general over in Washington, D.C., and they want a private to launch nuclear weapons over in San Francisco, they'll be able to make sure that the launch orders are able to be sent. But you have to remember, this was 50 years ago. When we think about the internet cloud now, we think about GoDaddy, and we think about Google, and we think about Facebook, and we think about Yandex, and we think about Alibaba and Tencent and the internet that it is today. But it wasn't the internet, right? Because it was 50 years ago. 50 years ago, right, that little internet cloud that they had was essentially government and military facilities. And so the idea back then was that this was a high trust environment, right? You had the government using TCP/IP version 4, Ethernet, all these standards. You had the military using this, and even initially, one of the interesting things when you look at the interesting arguments about the internet is the fact that basically this got created for the military, and then the very first people that went to after the military was the university folks. If you start to really understand the sociological implications of that, you start to see why there's so many philosophical loggerheads we run into in the modern world of technology. Essentially, the military creates something with the military mindset, with the military intention. And then the first kids they come have play with their new toys, where all the dope smoking college kids. Yeah, right. Became an issue. But anyways, the big thing to understand with the original internet cloud and with this networking, this was a trusted environment. So in the modern world with IoT, everything else going on with the internet and networking. Basically, we are in a zero trust model in the modern world, which is frankly very apropos for the 2020s. And what we mean by zero trust environment is that you can't trust, or you should not trust, any networking devices. It's not that you shouldn't trust Yandex. It's not that you shouldn't trust Tencent or TikTok or something like that. You shouldn't even trust the other devices that are on your internal network. The devices on your internal network may have been hacked by an outside actor. You may have an espionage agent in your environment. Actually, somebody to get hired by your company that also just happens to be getting a secondary paycheck by some intelligence gathering, agency out there. That may be happening. You may have malware in your systems. You may have a lot of different things going on. And so when you build your infrastructure in the modern world, you need to be building your infrastructure for a zero trust model. You do not trust anybody else on the network, right? That's a modern world. That's the 2020s. The important thing to understand, though, is back in the 1970s, that wasn't the world that we're in, and so all of the computer devices that were connected to the internet cloud of the time, they were considered high trust devices, right? These were computers that were in military installations. These were computers that were in government offices. There was computers that were even in, again, college research facilities. There wasn't malware like we have to. There wasn't really malware at all. Viruses and things, those are more things people were creating and playing with at the time. And so back then, basically every single computer device had its own internet routable IP address. When we talk about the 4,200,000,000 some odd TCP IP v4 addresses, the idea was there would be a unique IP address literally for every single device that was connected to the internet. So your local computer, your local host, right, the computer that you're typing your emails on, that would have an internet routable IP address. The server would have an internet routable IP address. Basically, everything more or less was connected to this really big network, and everything could communicate directly with everybody else if they wanted to. The problem that we ran into is that the internet that became more and more popular. It went from the college world, and then it then became a popular thing for more and more consumers. We start to have more and more people using the internet, and all of a sudden, those 4.2 billion internet IP addresses are not nearly enough. And so that's where we come up with the concept of network address translation. And so what network address translation allows you to do is it allows you to have internal private IP addresses. Again, when we talk about 192.168.1.x, that's a normal IP address range. 10.1.10.x is another IP address range you may see. And basically, these are internal IP addresses that you use for your internal network. So almost everybody, right, if you have a home network, you're probably running a 192 address or a 10.1 address. If you're running an enterprise, a business network, so you're probably running a 10 dot address because it has a lot more IP addresses in that particular subnet mask. But what NAT allows you to do is it allows all of these different networks to have their own internal IP address schemes. Then they connect to a router. All the computers in the network connect to a router that has NAT installed, network address translation, and then that router then has one single external IP address. So 208.66.44.1, let's say. So you have all of your computers underneath, and they're in the 192.168.1.x range. So you may have 200 computers all on your internal network. Whenever they try to go to some site like CNN.com, basically any of the computers in here, they will go through the router. The router will remember the IP address that the communication is coming from. It will then send the communication to CNN.com. When CNN responds, the router with network address translation will then route that communication to the appropriate computer on the internal network. And so that's how NAT works. All NAT is doing is essentially you're able to share that external IP address amongst all of the tens or hundreds or thousands of computers in your internal network. This is why we no longer have to go to IPv6, because now every external IP address, that can be an identifier for a network that, again, may have 10,000 computers inside. So instead of one IP address matching one computer, you have one IP address matching 10,000 computers, and all of a sudden, that 4.2 billion IP addresses is no longer such a significant issue. And so this is what we're talking about with network address translation. Back in the day, every single device that was going to be communicating with the internet, basically with this TCP/IPv4 network, they would have internet routable IP addresses. Again, because everything was essentially known equipment at that time. Now with network address translation, what we're able to do is we're able to have this internal IP address scheme that allows us to configure our network however we want internally. Those internal addresses, when we talk about the 192.168 or the 10.1, those are non-internet routable. If somehow these IP addresses get out onto the internet, they're actually broadcast to the internet for some reason, basically all internet class networking equipment will not route any of that communication, because they know that that's private. Those are private IP addresses and should not be routed on the network. And so that's really all network address translation is at the end of the day. So that's network address translation, essentially being able to share one internet routable IP address with tens or hundreds or thousands of computers on your internal network. The NAT software basically built into your router knows how to route the communication. So when your computer goes out to communicate with CNN.com, whatever traffic comes back from CNN.com will go to your specific computer. If the person right beside you goes to Breitbart.com, all the communication will get automatically go to their particular computer, and that's all just set up. That's done within the NAT software. I will say with this, just so you understand, NAT, for most people, I don't think there is anything to configure. I have to be careful with this. Again, this is the technology world, so you can't say never or you can't say always. But I have to say, in my life, there really isn't anything that I would configure for NAT, network address translation. It is just one of those things that just works. It is built into your networking equipment. If you have a router for your home, you have a small business router, you have a mid-sized business router, all this kind of stuff is just auto configured for you, so you don't really have to worry about much with the standard network address translation. The one issue you get into, though, is the issue with TCP ports, right? So we talked about IP addresses before. So when we talk about an IP address, 192.168.1.2, with the IP address, you get the identifier for the computer, and you also get the identifier for the network, right? Your subnet mask, I said that word again, but your subnet mask is what shows you where the network identifier ends and where the computer identifier begins. So if we have an IP address of 192.168.1.2 with a class C subnet mask of 255.255.255, we know that the network ID is 192.168.1 and the computer ID is 2, right? Basically, that's how the subnet mask works. But one of the important things to remember when computers are communicating is that there's an additional component for the communication, and that is the port number. And so what the port number is essentially all of the different server services, the computer services that are offered on the network. Those use specific TCP ports so that the computer knows how to interact with those particular services. If you're dealing with HTTP, TCP, you deal with port 80, right? So you may see this maybe sometimes in a web browser. You might put in something like 192.168.1.2, and then you do :80. What that says is I want to go to 192.168.1.2 IP address, and then I want to connect at port 80. Sometimes you'll see with this with HTTP where somebody will set the port to like port 8080 for some reason, and so you do 192.168.1.2 port 8080. You put that in your web browser, and then you'll actually be able to open up the web page for that particular computer. You'll see this sometimes again with web browsers when you deal with things like digital surveillance systems or maybe voice over IP telephone systems. Sometimes they decide to put that HTTP port on a different port number. Just, I don't know, because they got bored and they're giving you a different port number. And so that's one thing that you may see is when you go to connect to a computer or a service on a computer using a web browser, when you look at the documentation, they may tell you to use a specific port, and basically you just put that IP address in, and then you put that port number. And so basically with the ports, again, so every single service has its own port number. HTTP is port 80, right? SSL is port 443, correct? I'm thinking Simple Mail, SMTP, is that port 25? I forget. I've done this stuff along. There's so much memorization. I think it's port 25. FTP is that for port 21. Right? They all have their own different port numbers. The important thing with this is to go back and remember the world as it was back 50 years ago, right? Back 50 years ago in the hipster days or the hippie days of 1973, right? Everybody trusted everybody else. Peace, love, and happiness, or whatever, right? And so basically all of the computers that were connected to the internet back then, they all had their own internet routable IP addresses. And the important thing with this concept, though, is since they were all directly connected to the internet, all of their ports were freely available to the internet unless a firewall or something was configured, right? So if one person over here, right, they were at 203.66.44.1, let's say, and you have an IP address here of, I don't know, 209.77.66.4, if somebody, the 203 person wanted to go through the internet and connect to the 209 person at port 21, that was just there, right? There was no additional thing that they had to do because everybody was on the internet. And so not only was their IP address available to everybody else on the internet essentially, but all of their ports were available for anybody who wanted to connect to whatever port 21, port 25, port 80, port 443, whatever else. Here's a problem, though. Here's a problem with NAT, network address translation. With network address translation, we have one external IP address, 203.66.44.1, let's say. That is the external IP address for our router that has NAT installed onto it. And then internally, you have tens or hundreds or thousands of computers under the IP address, the private IP address scheme that you have internally. Again, 192.168.1.x IP address scheme, right? So in this, you may have IP addresses that go all the way from 1 to 254. So if you have a computer on the outside world and they're trying to get to your web server, that's behind this firewall that has NAT. The issue that we run into is that this router does not initially know where to route particular traffic, right? So if traffic comes in at port 80, the question then becomes, what happens to the traffic coming in at port 80? It hits the router, it hits the external IP address for the router, and then the router has to know where to send this traffic. And that's where you have TCP Port Forwarding. And so all TCP Port Forwarding is a configuration within your router that says anything that comes in for this port, so anything that comes in for port 80, I want you to direct it to 192.168.1.10. So all port 80 traffic will get routed to 192.168.1.10. That happens to be your web server. So if somebody goes to your IP address with port 80, they will then get your website. If we go up here, we can take a look at a configuration page. So this is an old configuration page I would have seen back 10 years ago from good old Linksys over there. So if you go into your home router, a small business, medium-sized business router, at some place you'll see something that looks like this, and this is for port forwarding. You may see this under the application and gaming tab. You might have to go in there and you may have to do like a Google search to see where it's stored for your particular small business router, your office or small business router. But basically somewhere in there will be something about port forwarding. And so with this, what you'll see is there's an option for your port range. So with the port range, some services require a range of ports. They might require from port 100 to port 200. They might use a number of ports for some reason. Again, digital surveillance systems, a lot of IoT type stuff. Sometimes they need port ranges. So basically, you would plug in your port range here. If it's not a range, if it's just a single port, you would just do like 25, 25, and that would be the single port. It asks you whether this is for TCP or UDP. So TCP is the transmission control protocol. This is where acknowledgments are sent back and forth. The SYN acknowledgement, the acknowledgement. So this is what you're standardly going to do. UDP is basically the communication without the acknowledgments. You might want this for things like real-time communication. So it'll ask you, do you want this for the port forwarding for TCP? Do you want it for UDP? Or do you want it for both, as they have here? And then basically here, what you'll see is it asks for the IP address. This automatically plugs in the range that is already configured on your router. So when you're setting up your router, it'll either ask you for information or it'll have default information for what your network looks like. So for this particular router, it's already set up for 192.168.1, and then all you have to do is plug in the computer identifier, that final number of the IP address for the computer you want the port to be forwarded to. So 10. So 192.168.1.10, we would want port 80 getting directed there, and then you would enable. This is a big one, especially on the small business routers. A lot of times you have a checkbox for enable. So you might go through and configure everything else and then forget to enable it. Seen that in the real world, done that in the real world, so be careful there. And basically, as soon as you do this, now anybody that comes to your network that hits this particular router, if they're coming in at port 80, the router will automatically route them to 192.168.1.10 on your internal network. And then from there, as long as your Apache or your Nginx web server is set up properly, then they should be able to get your website for you. And so this is all TCP forwarding is, and we need, or TCP port forwarding. And the reason that we need TCP port forwarding is now that we're using one external internet routable IP address for tens or hundreds or thousands of computers. Basically, if traffic is coming from the outside world into your router, your router needs to know where to send that traffic. So there you go. That's really all there is to NAT, network address translation, and TCP port forwarding, right? This allows us to have one external IP address that is able to be used by hundreds or thousands of internal IP addressable devices. And basically this means that we don't have to go over to IPv6 anytime soon. Again, it's one of those band-aids. It was a band-aid that was slapped on, a couple of decades ago, and it's working so well. We're all just going to assume it's a fix that we don't have to worry about anymore. Again, a big thing to understand with network address translation is for the network address translation component itself, I've never had to configure that. An important thing, this is kind of one of those things that's just in your router. All routers at this point, 2020, all routers should have it. Maybe yours doesn't. If you're using like Cisco equipment, if you're using high-end Cisco equipment, they may not have it. But any kind of small business router, any kind of home router, it'll just have this network address translation already installed, and it will already work for you. I'm not going to say you can't configure it at all, but I don't know. I've never configured NAT beyond turning the damn thing on, to be honest with you. But the important thing you do have to understand with NAT is that if you're going to have internal server services where people from the outside world are going to be trying to gain access to your server services, you are going to have the port forwarding configured. And so what port forwarding says is, okay, if somebody from the outside world connects to the external IP address and they're connecting at port 80, the router will then automatically route them to whatever your web server is, 192.168.1.10. Let's say, if they're trying to connect to your email server, so if you're still running your own Exchange email server, something like that, you have external email clients. Maybe they would connect to the external IP address, and then port 25 or whatever port the Exchange server uses, that would get automatically forwarded to the IP address of your particular Exchange server. The important thing to understand here, though, is like when I talk about this, so if you have somebody that's internal, so somebody is in your internal network and they are going to go out to CNN.com. When they go out to CNN.com, there is no configuration in NAT for the response from CNN.com to get auto-routed back to your computer. So the router keeps track of who internally is talking to who externally, and then make sure everything routes properly. When we talk about the TCP port forwarding, these are people in the outside world that are initiating the communication with your internal computer services. And so that's why you need that particular port forwarding. One of the big issues that you're going to run into when you use NAT is that when you do port forwarding, more or less, again, not everything is absolute in the tech world, but more or less, when you're doing port forwarding, one port will go to one IP address. So if you have a cluster of web servers, or if you have a cluster of some other different types of servers, one of the important things to understand is that for basic port forwarding, you are only going to be able to route to a one single IP address. And so that's one of the things that you're going to have to figure out when you're building out your own internal infrastructure, figuring out how that works out. You may use some kind of reverse proxy server, which is a word, keep that in the back of your head. There's something called a reverse proxy server. Anyways, you may connect to some, basically, there's ways that a number of computers in a cluster can essentially share one single IP address. And so you may have to build it that way, but it's just kind of one of those things to keep in your mind. Another thing to be thinking about, I've talked about before, that when you create your internal IP address scheme, that you're going to have some computers or networking devices that have static IP addresses, where most of the computers on your network should have DHCP addresses. So DHCP is Dynamic Host Configuration Protocol. What this does is it automatically assigns the IP address, the subnet mask, the default gateway, primary and secondary DNS servers to new devices that connect to the network. One of the big things to understand is many times when you look at the port forwarding configuration panel, that it will ask for an IP address, not a computer name. Right? So if your router asks for a computer name, you could plug in server or web server, whatever the computer name is for your server. If it asks for a computer name, then that server doesn't necessarily have to have a static IP address. It can have a dynamic IP address because it's looking for the computer name, not an IP address. An important thing to understand, though, is that if you have a server and your port forwarding configuration only allows for IP addresses, then you need to make sure that that server has a static IP address, that IP address never changes. Because if you have a web server for the website on your network, You just grab a DHCP address from the DHCP server, you plug that into port forwarding, and then you call it a day. Or your intern calls it a day because they don't think about it, right? It's like, oh, what's the IP address of the web server? Let me do ipconfig or ifconfig. Okay, ifconfig. Okay, it's 192.168.1.55. You plug that into port forwarding, you walk away. Well, if .55 was provided by a DHCP server, at some point you're going to reboot that server, or the power is going to fail. Something's going to happen. You're going to reboot that server. And then DHCP might give that server an entirely new IP address. And now the port forwarding is going to .55 and your web server is now .67, and somebody gets to do some fun troubleshooting. So this is an important thing to be thinking about. Again, when you start thinking about your DHCP, there's something called a DHCP scope. So for dynamic host configuration protocol, you go in, you talk about, you can configure the length of the leases for the IP addresses, all this other configuration. One of the things is the scope. So basically, what IP addresses are available in a pool to provide to clients that connect to the network. And so many times for me, if I'm using the 192.168.1.x networking scheme, what I will do is I will reserve 192.168.1.1 to 192.168.1.20 at least, and then give everything else to DHCP. Then I have those 20 IP addresses, those 20 that I'll use for static IP addresses, and some of those I'll use for the networking equipment, some of those I'll use for the servers, some of those I'll use for things like the printers. A lot of times it's better to have printers on static IP addresses. Makes life a little bit easier. And so that's just one of those things to be thinking about, because again, if you have your servers dynamically getting IP addresses, that can just cause a mess for the network. And this is also, when I start talking about this, I think you'll start to understand a little bit more about why the OSI model is so important. Again, one of the things I talked about before with the OSI model is so many people look at the OSI model and they think, oh, this is just something I have to memorize for a test. I'm going to memorize this for a test and then I'm going to forget it. But look, when we start talking about all of these different configurations, all of these different things that can be done on your network, you start to understand how troubleshooting problems with your computers and servers can become ever more complicated. Again, layer one on the OSI model is basically, did somebody unplug the network cable? Which, to be clear, is what happens 99.9% of the time. But then past that, it may be something on the switch level. Beyond that, it might be something at the IP address level. Again, the default gateway. So the default gateway is if you can't find the computer on your network, then the default gateway is the IP address of the router your computer should use to look at the internet or the wide area network. Did somebody fat finger that and put in the wrong default gateway? Then as we start going up, again, we go into level 4, level 5, level 6, level 7. That's where you start seeing like things here, such as port forwarding. So that's the thing, is your server may work. So your server works, your server is connected to the network, your server can see the internet, right? All of that's working. Internal to your network, if anybody internally tries to go to your server, they see the website that they're supposed to see. But when somebody from the outside world tries to go to your server, it fails out for some reason. And so that's one of the things where that might be a TCP port forwarding issue, where for some reason TCP port forwarding isn't enabled. So you're not able to actually set up the communication between the two devices. And so this is where, like I say, that OSI model makes things a lot easier for you to do troubleshooting. It's like, okay, I'm at the server, my server can see everything, my server can get to the internet. Okay, that's fine. Okay, let's see. Internal to the network. Can computers that are internal to the network see the server, and can they access the services that they're supposed to access? Okay, that's working. Okay, so somebody that's external to the network, right? That's where you start doing the troubleshooting procedure to try to figure out where is the problem actually occurring. So, anyways, there you go. There was network address translation for you and TCP port forwarding. Good, fun, interesting things that hopefully won't melt your brain. It's fun, it's interesting, and it doesn't melt your brain. So we'll have some more of these relatively easy classes, non-brain melty classes, until we get back to the brain melty class. The only final thing that I would leave you with is also one of the things that I want you to start understanding is how much building your network and your infrastructure becomes an art form. One of the things I talk about a lot is when you're going to be building out your infrastructure, what resources do you have? What are the requirements of your institution? Like what resources do you have, like with IP addresses and all of that kind of thing? That is going to be that will determine how you are going to build your infrastructure. Again, if you have NAT. Right, if you have a router with NAT, and so all of the internal computers are sharing an external IP address, but then you have a web server, but you have a web server service that you want to have very redundant, very reliable, you may then want to create a cluster of web servers. But with port forwarding, you can only forward to a single IP address. So that's, as I was talking about, where you might use something called a reverse proxy server. Essentially, a reverse proxy server, on its external side, you have one IP address, so the TCP port forwarding can forward that IP address, but then a reverse proxy server then internally to it can connect to numerous other servers. It essentially is almost kind of sort of like NATing for like a cluster. And again, that gets us into its own world. But that's where I kind of want you to start understanding how much of building this stuff out is an art form. And also, with it being an art form, as somebody who has to maintain this crap, some people aren't very good artists. Again, that's one thing to really understand, like with how this stuff works. The basics, like TCP ports, that's a science, that's engineering. Subnet masking is a science engineering. But a lot of how this ends up getting built is art. And so one of the things that you'll run into as a maintainer is the person who built this particular piece of art only half knew what the hell they were doing. And so many of the problems you may be running into are based off of how that infrastructure was initially designed. And no matter how much work you do, even if you work 100 hours a week, the design, maybe the fundamental design of what was created might be so failing that it's always going to be a quirky as hell architecture. So one of the things that you need to be thinking about is when you look at your own infrastructure, when you look at your own architecture, do you actually believe it was designed for stability? Because many times it was band-aided together and then somebody walked the hell out the door. And so one of the things you're going to have to decide as a professional is do you keep slapping band-aids on what was previously built? Or do you do the hard work of ripping out what was previously built to rebuild the infrastructure in a way that will actually support your requirements going forward? But that is a class for another time. So as always, I enjoyed doing this particular class and look forward to seeing you in the next one.